When we analyze random variables, we have to think about what a random variable is. A random variable is numeric. Its value depends on random outcomes, which may or may not happen. There may or may not be equal probabilities of those outcomes, and we want to analyze those outcomes within the context of probability. And so the first idea that we're going to look at is what's called a cumulative distribution function. This is often called the CDF. The value of the CDF is a number between 0 and 1. 0 represents a probability. 0% of the outcomes are less than or equal to some value small x. X is a potential outcome of the random variable. So if we look at this fourth bullet point, think of X as being a potential outcome of a variable and X being the random variable. So if I flip a coin and assign 1 to heads, 2 to tails to make it into a random variable, to make it numeric, 1 is small x. The 1-2 set, the coin is large X. So think about a 20-sided die. There are 20 different small x's, 1 through 20, and the outcome of the die is a random variable. So whatever is realized is the random variable, and there are certain probabilities for each of the outcomes of the random variable. Now, this is what we call a discrete random variable, in that we can count the number of outcomes. So let's take a look at the cumulative distribution function. It's large f of x. It's the probability that the value of the random variable is less than one of the particular outcomes of the random variable, less than or equal. So if we think about the 20-sided die, let's say the first outcome is 1. What is the probability that the random variable will be less than or equal to 1? Well, there's only one of the 20 outcomes that corresponds to 1, that's 1, and so 1/20th is the probability of getting the outcome of the random variable to be less than or equal to 1. Now let's take a look at an outcome of 13. There are 13 outcomes that are less than or equal to 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. The cumulative probability of getting something less than or equal to 13 is 13 out of 20, 65%. Now, this is true not just for equally likely outcomes. Let's say we have a random variable that takes the value 1 with probability 0.1, 2 with probability 0.7, and 4 with probability 0.2. So 100% of the time it'll be a 1, a 2, or a 4, but the probability of 1 is 0.1, the probability of 2 is 0.7, and the probability of 4 is 0.2. What is the cumulative distribution function for f of 2? Well, it's 0.1, 1 is less than 2, plus 0.7, 2 is less than or equal to 2. That's 0.8. So we add the probabilities of all the outcomes less than or equal to x, and f of x, large f of x, spits out that sum. So the cumulative distribution function is one way to describe the random variable, in that it describes an area where many of the values are to occur. Now, the probability density function we call small f of x, and it tells us the relative probability that the value of a random sample would take that sample. So it's the assignment rule for the probability to the random variable. Now, we call it small f of x dx. Dx is the range of values of interest if it's continuous. And we define this within the context of a mean, mu, and a variance, sigma squared, for a random variable. And what the probability density function does that differs from the cumulative density function is the probability density function is a description of the mapping of the probability to a particular outcome. So think of it as the assignment rule. The cumulative density function just tells us, hey, take a look at these outcomes. How likely is it that you have something less than or equal to a particular outcome? That is, so if you think about it, when we had the discrete random variable where 0.1 was the probability of 1 and 0.7 was the probability of 2 and 0.2 was the probability of 4, 0.8 was the CDF for 2. 0.7 is going to be the PDF associated with 2. Okay, and so those are different things. So with a continuous probability density function, we think of the probability density function as being the derivative of the cumulative density function. And the most famous one is associated with the normal distribution. And I point out what it is here. The normal distribution is characterized by a specific functional form, e to the x, and it's parameterized by mu and sigma, the mean and the variance. So when Excel is calculating the PDF for a normal distribution, it uses norm.dist. False is the PDF, true is the CDF, and we're normally interested in stats 1 and stats 2 in the CDF, but we could potentially look at a DX and look at a PDF. So we could look at something like the assignment rule for a particular space. The PDF is important because it allows us to compute the expected value of X. And we're going to look at that later on. So what I'm just trying to get across here with the cumulative distribution function and the probability density function is that those are some descriptions of the percentage of outcomes that are less than a particular outcome and the assignment rule that gives probability to particular outcomes. Those are different things. So let's go back to the idea of the random variable. It's numeric, its values depend on a random outcome, some of which may be more likely than others. There is a true population mean for the random variable denoted mu. So we're thinking right now in terms of the random variable as being a feature of a particular population. So I think the random variable x is completely described by the probabilities of X. I don't need to sample. We're not considering sampling or collecting data at all. We're just saying, hey, X behaves in this way. There's a mean expected value of X, call it mu. And we know the probability assignment rule, all the probabilities for all the outcomes and how likely they are. So when we calculate a population mean mu, we think of it as the expected value of the random variable. And it's a weighted average of the probabilities and the outcomes, and that average doesn't actually have to correspond to any particular outcome. So if I roll a die, I have a 1/6 chance of all the faces from 1 to 6, but if I take the expected value of the die as 3.5, and that is not an outcome on the face of the die. So let's take a look at a discrete PDF. This is slips of paper. Let's just pretend there are 3 slips of paper in an envelope, 7, 7, and 12. So 2/3 of the time you get x equals 7, 1/3 of the time you get x equal 12, and 7 and 12 are the 2 possible values of the random variable large X. Now the PDF of x equals 7 is 2/3. The PDF for x equal 12 is 1/3, but the CDF for x equal 12 is 1. So there is a difference between the two. And f of x is you take the function and it is an assignment rule for all the outcomes. In this case, there are just two outcomes, 7 and 12. And the assignment rule is those specific probabilities based on how likely you are to pull those slips out of the envelope. So when I think of the probability density function, the rule is very simple. This is kind of trivial in this case. I'm pulling two slips out of the envelope that are 7 and one slip that is 12. That's the rule. When we deal with continuous variables, the rule is a function because the outcomes are not countable. So for example, if you have like a uniform distribution, even though the bounds of the uniform distribution are not from minus infinity to infinity, even in that small space, you have an infinite number of outcomes. So we can calculate the expected value with probability based on the given probability assignment rule from the probability density function. So we can calculate the average, the expected value here, and this is mu. So here x is discrete. In the previous instance, x was continuous, and we're not going to calculate expected values of continuous probability distributions because that requires integration, which is outside the scope of this class. But we can do it for discrete random variables like this one. So let's say x is discrete. That expected value of x is the sum of the probabilities times the outcomes. So I have probability times outcome, and I add it up for all the different outcomes. So there are n outcomes for x. And xi here, small xi, represents the outcome. P represents the probability. So we have, in this example, where we have 3 slips of paper in the envelope, 7, 7, and 12, there's a 2/3 chance of getting 7, so the probability of 7 is 2/3. 7 is the xi. So I have 2/3 times 7 plus 1/3 times 12. So I have 14/3 plus 12/3, that's 26/3, 8.67. Okay, so the expected value in this case is not an outcome of the random variable. It is in between the two outcomes of the random variable. Note the median of this is 7, so the expected value is different from the median. So the median was one potential way of measuring the center, but the expected value is different. This is how to calculate an expected value for a discrete probability distribution. You take the probabilities times the different outcomes x, and you add them all up. The set of probabilities in x's is the probability density function. Expectations are linear. So suppose you have two variables, x and y, and they may or may not be independent. So if x is the temperature on Sunday and y is the temperature on the subsequent Monday, then they are probably not independent because they are correlated with whatever the weather patterns are in the area. However, if y, instead of being the temperature on that Monday, if y is the number of stuffed animals in a zoo toy shop, then we could say, oh, okay, they're independent. So let's look at x plus y. And let's suppose that x can take random variable values, as can y. So let's go back to the envelope, keep it as x. 2/3 of the time you get 7, 1/3 of the time you get 12. Now suppose you flip a coin, and 1 is heads and 2 is tails. So half the time you get a 1 and half the time you get 2. Let's call that coin y. So we have an envelope where 2 of the slips are 7, 1 of the slips is 12, and a coin where heads is 1, tails is 2. X plus y takes the value of 8. You get a 7 in the envelope and a 1 with the coin. 9, 7 in the envelope, 2 in the coin. 13 is 12 in the envelope, 1 in the coin. And 14, 12 in the envelope, 2 in the coin. What would we expect the value of x plus y to be? So suppose we define z to be the random variable x plus y. Well, what is the expectation of x plus y? Well, we have a couple of ways of going about doing this. We could construct a probability tree where we have 2/3 of the time we get a 7 multiplied by 1/2 of the time we get a 1. And so 1/3 of the time we get 8, 1/3 of the time we get 9, 1/6 of the time we get 13, 1/6 of the time we get 14. We could add all that up based on the probability tree. You can see that this might be a bit challenging if we had a number of outcomes. So instead of having 2 outcomes of the envelope, what if we had 12 outcomes of the envelope? Then the number of branches of the probability tree would be extensive. Or we can exploit the fact that expectations are linear. So here's an important definition for random variables. If I have 2 random variables, x and y, even if they are not independent, the definition of the expected value of x plus y is the expected value of x plus the expected value of y. Now we already know the expected value of x is 26/3. The expected value of y is 1/2 times 1 plus 1/2 times 2, because 1/2 and 1 and 1/2 and 2 are the probability density function for y. You add 26/3, that's the x, plus 3/2, that's the y, and you get 61/6. That's the expectation of x plus y. So what we've established so far is that I can create some random variables from other random variables. I could generate a new random variable by just adding a couple of random variables together, and I could have an idea of what the expected value of that new variable would be based on the expected values of the old variables. Now let's have a look at what's called variance. So if we go back to the probability density function for the normal distribution, it's characterized by mu, which is the expected value of x, and sigma squared, which is the variance. The variance is a useful concept in statistics, it's a useful concept in regression, but it's also a deep parameter for population random variables. So we care deeply about the variance. To illustrate this, just think about the quality of any food item that you purchase. We probably want that quality to have low variance. You want to know what you're eating. If it has high variance, then even if the expected value is high, the food's really good. On average, there are still a non-trivial number of outcomes that we don't like. So the variance is a mechanism of describing how far all the outcomes are away from each other, and to the extent that we care about a subset of particular outcomes of the random variable, we would like to know more about the likelihood of their occurrence from the variance. And one other potential way of doing that is calculating the CDF for the particular set of outcomes that we're interested in. However, the CDF is going from left to right. It's going from the smallest value up to x. So we don't really get a sense of the largest value down unless we calculate 2 different CDFs. And even then, you don't get an idea of the magnitude. So the CDF is a lot like the median in that way. And so that's just something we have to keep in mind, is that sometimes we need something that even better measures the outcome than, say, a cumulative distribution function or a median. All right, so the variance is called sigma squared. It's the expected value of the random variable x minus mu, that's the mean. Now, we defined mu previously to be the expected value of x. Okay, so it's the expected value of x, that's the random variable, minus the expected value of x squared. So expectations of x, I expand the square, minus 2x times the expected value of x plus the expected value of x squared. So I'm expanding here. I'm expanding this quadratic formula. 2, once I distribute this expectation operator in here, I have 2 expected values of x squared. So I have minus 2 expected value of x squared plus expected value of x squared. One of those cancels out, leaving me with the expected value of x squared minus the expected value of x squared. So this is mu, and this I'm squaring the values of the random variable. So let's go back to the envelope. The expected value of x squared is 2/3. 2/3 of the time I get 7, which is now squared, plus 1/3 of the time I get 12, which is also squared. So I have 49 times 2/3, that's 98 over 3, plus 12 squared, which is 144 divided by 3, which is 144 over 3. So I have 144 plus 98, that's 242 over 3, which is 80.67. The expected value of x squared is 26 squared divided by 3 squared, so I have 676 over 9. Okay, and if I rearrange, if I create a least common denominator here, I can actually clean this up a little bit to get 50 over 9, which is 5.56. So the expected value of x squared minus mu squared is the variance. Okay, and for a discrete probability distribution, you take the probability times the outcome minus the mean squared. And that's what we did here. Okay, so we did a discrete probability distribution, but we evaluated this formula directly. Let's have a look at another concept called covariance. So let's suppose we create this new variable z, which is associated with x plus y. Now let's redefine x to be 3 or 4 with equal probability. Y is 1 or 2. The probability that y is equal to 1 is 0.75. The probability that y is equal to 2 is 0.25. So 1 is more likely for y. X could be 3 or 4. The variance of x plus y, you can add the variances of x and y together, and you subtract 2 times the covariance of x and y. So the covariance is a measure of how x and y vary together. So when x moves in a particular direction, does that increase or decrease the likelihood that y moves in that direction? Well, if it's positive, it increases the likelihood. If it's negative, it decreases the likelihood. And if they're independent, then x's movement has no bearing on y, and the covariance is 0. So the covariance of x and y I can find by taking the probability of x minus the expected value of x times y minus the expected value of y. And to do that, we need to find the expected value of x and y. The expected value of x is 50, 50, 3 or 4, so 3.5. The expected value of y, 1 is a little more likely, so it's 1.25. Now, I have some probabilities associated with x and y, so I treat x and y as a pair together. I'm observing x and y simultaneously. So suppose that you only observe y equal 2 when x equal 4. So high season, both x and y are good. And then high season lasts a little longer for x than it does for y. So when I only observe y equal 2 when x equal 4, the probability of x equal 4, y equal 2 is 0.25. So every single time y equals 2, x equals 4, and this whole 0.25 is associated here. The remainder of x equal 4 is associated with y equal 1. So 0.25, 50%, I split it into 0.25, y equal 2, 0.25, y equal 1, and then 0.5, y equal 1, x equal 3. And there's never an instance where I see x equal 3 and y equal 2. Now, let's take a look at the covariance. 50% of the time, I see x equal 3, y equal 1. So every single time y is equal to 1, x is equal to 3. Okay? Here I take 3, I subtract the expected value of x. I take 1, I subtract the expected value of y. I multiply by 0.5. Then I do the same thing for when x is equal to 4 and y is equal to 2. 0.25. Subtracting expected values. Then I do the same thing for when x is equal to 4 and y is equal to 1. subtract the expected values. I do the same thing for when x is equal to 3 and y is equal to 2. It's just the probability of that occurring is 0 because when x is equal to 3, y is never equal to 2. I split this out, and I have 0.0625 plus 0.09375 minus 0.03125. I get 0.125. Okay? Now, let's take a look at the covariance here. And actually, I'm going to go back really quickly and fix these slides. I believe I subtracted only one covariance on the slides. Let me clean that up here on the slides. Open them back up here. I use LaTeX to make the slides for this class. So there we are. I'm going to recompile the slides, then open them back up, repost these onto CourseDen. There we are. Now let's go back to open that back up. There we are. Okay. And this should actually be .25. One more quick math check. There we are. Okay, so we've calculated the covariance. How do we find the variance of x plus y? Well, we find the variance of x plus the variance of y minus 2 times the covariance of x and y. Well, we have the covariance of x and y, so that's nice. When the covariance is 0, x and y are independent, so I can just add the variances. But because the realization of x has no bearing on the realization of y. But that is not the case here. So when y is 4, x is 2 all the time. So every time I see x equal 2, it's going to explain a lot of the movement in y. And so I don't have additional movement in y when y is equal to 4. It's all explained by the value of x. So the value of x, in a sense, determines when y is equal to 4. And so I want to get rid of a lot of that variation in y. In fact, it's all completely determined by x. And I do that here. I calculate the variance of x. I show you right there. We use the formula. Okay. I do the variance of y. Same deal. Variance of x plus y. I subtract out 2 times the covariance, which was 0.125. 2 times 0.125 is 0.25. And that's the variance of x plus y. So we've spent a lot of time dealing with random variables as descriptors of the population. This is an important concept. So think of the population as the collection of all values of a random variable. So I've got all the values of the random variable are accounted for in the population. And when I'm analyzing the population, if I had full knowledge of the population, I would have all of the probabilities as well. That is just not consistent with real life. So in real life, data are observational. So I don't even know what the possible values of the random variable are. So I only see a subset of x of the random variable. So I see a subset of x and I don't observe the probability. So I don't know what the values of the random variable are in the population, okay? And I also don't know how likely the outcomes are. And so when we think about sampling, I'm taking a collection of observations of the population, but then when I'm trying to analyze it, I use statistics to conduct inference about the mean. I'm trying to do a couple of things. I'm trying to learn, like, what are the values of the random variable, and I do that by sampling, and then I'm trying to assign probabilities to those as well, and I do that with sample mean and sample variance. So if we think about what sampling is trying to do, sampling is saying, hey, look, you know, if you knew the probabilities and the values of the random variable, you would analyze them using this expected value formula, this variance formula, this covariance formula. The problem is you do not know those things. So you have to estimate, we're trying to estimate the true population mean mu from information from the sample. And so sampling matters a lot. We care about population parameters in deep ways. So just consider how important watching this video is. Rate it from 1 to 10. Okay? Let's say I estimate the value of this video from publicly available likes versus dislikes. So if there are a bunch of dislikes in the video relative to the number of likes, I think the video is not helpful. In fact, when I go online to look at videos on YouTube, probably one of the first things you notice is the percentage of likes versus dislikes. So if it's like 5 to 1, 6 to 1 likes, hey, this is a good video. If it's like 3 to 2, I have some concerns. There are a large number of people that didn't find the video to be particularly helpful. Somebody's tweeting on Twitter and they get ratioed. We all know what that means. And more to the point, it's an estimate of how people perceive the sentiment of the tweet. So we're always using these samples as estimates of the true quality or the true population parameter, but maybe we don't think of it in that way. And so we need to. So let's look at the sample mean. Let's let X bar be the sample mean. And I take each observation, I add them all up and divide by 1 over n. But here is what I want you to think about with the sample mean. 1 over n, reconceptualize it as a probability weighting of the observation. So I collected some data. These are realizations of a random variable. And how I calculate an expected value is I take PI and use 1 over n as my estimate for PI. So I use 1 over n here as my estimate for this probability. I don't know what the true probabilities of the outcomes are. I'm using 1 over n as my best estimate. So this is an unbiased estimate of the population mean, but it may not yield the true probability density function estimate if we knew the probabilities and the outcomes, because we don't know the outcomes and we don't know the probabilities, so we observe some of the outcomes and we just estimate the probabilities 1 over n. And so you can think of almost any time when, even if you were to flip a coin 20 times and you know what the outcomes are, and we know the probability is 1/2, but still, if I go through the process of constructing a sample mean, it's unbiased, but I may not get 1.5 as the sample mean. The sample variance, but the fact that I don't get 1.5 is actually a problem for the sample variance because the sample variance is biased down. And I show you why on these slides. I go through a little bit of a derivation of the expected value of the sample variance. But what I want to get across is you got to take the square root here. I'll put that back on the slides. But we correct the sample variance by 1 over n minus 1 because when we expand our expected value of the sample variance, this expectation of x times the sample mean, there are instances when I just have the population mean squared, but then I also have some variation. And so that is why we have some bias. But for the purposes of this class, we are just going to calculate the standard deviation, and we take the square root here. That is an estimate of the population variance.